in this case, the ones that fit are h and k and a, right? So we know h and k because we have the coordinates of that point right there, which are what? -4, +2. So that's just h and k. So we get 2 of the 3. We just need the third, right? And so we had some techniques for that. Now, the one that always works, remember, is if I can plug in -4 for h and 2 for k, I still need to find a, but if I have another solution of this function, another point on the curve, in other words, I can plug in those x and y values and solve for a, right? And then I've got all 3 of those parameters. And remember, we kind of talked at the beginning of the year, for a line, or in this case a parabola, the parameters are like the values that you have to dial in to create that parabola, right? By dialing in values, specific values of a, h, and k, we're going to form this parabola, right? So that's how we could come up with those 3 quantities. It's in vertex form. It'd be really simple to put it into general form, right? All we'd have to do is just expand out that binomial, either by foiling it, or if you know we'll talk more about expansion patterns next chapter. But we could always just FOIL that out. X minus -4 would be x plus 4 squared. Expand it out, distribute the a that we found, add up the like terms, and we're done. It's in general form. Okay, this is almost the same problem. Almost. What do you think? Yes, got it.
How do we know which point is like where on the parabola?
Okay,
We have
so
to graph it and figure it out?
you mean, say it again?
We have 3 points, but how do we know which one's the vertex and which one's the
Ah, okay, good point. On this next problem we're doing.
Yeah.
Yeah, okay. Well, very good question. We don't know that any of those are a vertex, do we?
No.
You know. Ah, okay, but look what we've got.
I can never remember the name of this equation, but.
Okay, we do have intercept form, right?
Yes.
We do have, or factored form, we do have some special points here that we can't recognize. Because we've got these y values are 0, what does that tell us?
They're on the same.
They're on the x-axis, right? So those are the x-intercepts with the zeros, right?
So then that means 7, -6 is not the vertex.
Is not the vertex. It might be, but we don't know. It could possibly be. But it's just some other point on the curve. But what is this telling us? What value does this tell us, that first point right there? It tells us that...
The vertex of x would be 5.
Okay, well, it does tell us that, but it tells us that the vertex would have an h value of 5, but we would have no idea what the y value would be, would we? Right? So we're kind of stuck. I mean, but that does tell us something. What value is that telling us? It's telling us one of the 3 parameters in one of the 3 forms. Which form did you say this fit? Vertex? No, not vertex forms. We don't have a vertex. Factored form or intercept form, whatever you want to call it, right? So this is what we have. Right?
Yep.
So we just need to find the values of p and q, and we're done. So what does this tell us? P is 4, for example, right? There's 1. What does that tell us?
Q is 6.
Q is 6. And so all we have to do then to find A is what? Yeah, good. Plug in the values of P and Q, which we know, and to find A, we would just substitute a value of x and y that we know lies on the curve, the solution, right?
What does P and Q stand for?
P and Q are the x-intercepts,
Okay.
right? So remember when we graph a parabola that's in factored form or intercept form, remember it always kind of looks like this, and so those are the values of P and Q.
Okay.
Remember that? Yep.
Couldn't you just use one of the, couldn't you just continue using 4, 0 or 6, 0 and plug that back into the equation?
Okay, no, you can't. You can't. Here's why. Look what happens if you do. So it's a good question.
Because then y is 0.
Right. It's going to, And there's a good reason for that. We'll kind of talk about sort of why the math gods insist that we use a different point. First of all, just look what happens if we do plug those in. We get y equals a times the quantity x minus 4 times the quantity x minus 6, right? Now, if I try to plug in one of the intercepts, what's going to happen? If I plug in, for example, the point 40, I get 0 for y, right? Equals a times 4 minus 4 is what? 0 times 4 minus 6 is negative 2. I just get back the equation 0 equals 0, right? Which is true, but it didn't help us out. It didn't help us solve for a, right? Yep.
So if they give us if they took out the 7, -6, we couldn't solve this.
You could not solve it, right? You couldn't solve it because you have to have 3 pieces of information to solve for those 3 unknowns, right? Here's 2, but we need another point to solve for the remaining unknown.
Wait, so how did we find, because the vertex, how did we find the vertex?
Okay, right, in the last example, how come we only needed 2? Because the vertex is a double whammy. The vertex gives us h and k, gives us 2 pieces of information. Each coordinate of the vertex gives us its own little piece of information, right?
Before, like, we find the zeros, now we can find the vertex.
We did, but now that was a different situation. That's when we actually knew what the function was, right?
Okay.
And so we could find the x coordinate of the vertex from the intercepts and then plug that back into the function to find the y coordinate, right?
Oh,
Okay.
But we don't have the function here. We're trying to find the function.
Okay.
Okay. Yeah.
Alright, on that other slide, what made the y 0 and?
Back to this guy.
Yeah, what'd you do?
Okay, so all we did, we know that we were given these 3 points, and so we recognized that when the y coordinate is 0, that specifies those are x-intercepts, right? Because they have to be on the x-axis. So those are the 2 places where our parabola crosses the x-axis, right?
Yeah.
So therefore, this fits this form. Now, if those had been different points, it wouldn't have fit this form. It wouldn't have been useful to us, right? But the information we're given matches that form of a quadratic function. Does that make sense? Okay, yes?
So for right now, will all of our points have at least 2 coordinates that have a 0 in them?
Okay, well, up till now they do, right? So the 2 examples we've looked at have been examples that specifically fit vertex form or factored form, right?
And this is
This is factored form, right? And so all we'd have to do to finish this up, does everybody kind of see what the last step is here?
Yeah.
We would take these coordinates right there, right? Plug those in for x and y, so -6 would go in for y, 7 would go in for x, and we would just end up with -6 equals a times 7 minus 4 times 7 minus 6, right? Okay. Listen, I got too much background stuff going on here. All we're trying to do is we got to find the values of a and p and q, right? So we can specify what is this function. The only variables we can have left in this thing are x and y, if we want to be able to have a function that we can graph or we could use as a model, right? So we have to be able to name what those values are. Because remember, when a changes, that changes fundamentally what the parabola is. When a is positive, it opens up. If a is a big number, it's tall and skinny, right? So we have to be able to, by changing those values, we're tweaking this parabola to be the one parabola that passes through those 3 points, right?
So we're trying to find.
So you're trying, our goal here is, we want to use this information to identify what the values of a and p and q are, so that we can come up with a function that fits this thing, right? We were given, because this fit the form, factored form, this works out pretty well. We were given 2 pieces of information that we need directly. We were given p and q, right? But we still have to find a, and that's where this other point comes in.
Okay, so then once you find A, then you.
Then we'll just, so let's finish this one up. So we'll find A.
And
Go ahead.
then if it's like on middle, our answer would just be the equation.
Yeah.
Okay.
Yeah, just be the function, right? So if we solve for A here,
What do you mean, like, it'd be the equation?
well, you'll see. So it's gonna ask you to, I didn't write that part up there, but what Moodle's gonna say is you fill in the blanks, f of x equals, okay, you're doing that. Okay, so if I solve for A, what does this become? 3, this becomes 1. So don't I just get negative 6 equals 3A? So what's A? Negative 2, right? So A is negative 2. We know what P and Q are. I just plug that stuff in and I've got my function, right? So Y just equals A times X minus P times X minus Q. That's it.
We don't need to put it in standard.
Well, okay, it's in factored form now. If the question asks for it in factored form, that's your answer. If the question asks for it in general form or standard form, we'd have to FOIL that out and distribute the negative 2. But that would be our answer, right? Okay, but, so that's no big deal, right? Those two are sort of handpicked to be easy because they fit those two forms. But what happens when that's not the case? Okay, this is actually a much harder problem.
Wait, our answer,
Go ahead, I'll go back. So our answer would be that.
that right there, so that exact question up top, that's it.
Yeah, well, that's the
If it's
answer.
factored form.
If it's factored form, right. If it were to say, like, for example, you'll see another one that'll look like,
What form?
so here's another one. Okay, they want this in general form, right? Okay, so this would be an example where now we do the same thing, but they want to have f of x written in general form, so we'd have to just expand that, put it in general form.
So it'd be
Okay.
x squared plus bx plus c.
Yeah, ax squared plus bx plus c, correct. Okay, so what about this guy, though? What about that one? Does that fit any of the forms? No. It's possible that one of those is a vertex, but we don't know, and so it doesn't help us, right? Those are just 3 random points. None of those are x-intercepts. None of those we know for certain is a vertex. So what's the only form that we could use to fit this to? Standard form or general form, right? Okay, so this is what we have to match this to. We have to match this to y equals ax squared plus bx plus c, right?
Yeah.
Okay, do you see why this is so much harder?
Yeah.
None of that stuff is given to us directly, is it? Right? In the other forms, we were able to say, aha, I know what P and Q are, or I know what H and K are. We just got to find one thing. Now we got 3 unknowns, none of which are given to us directly. So any ideas? What could we do here? I've got how many unknowns?
3.
3. So now, just think algebraically here. How many different equations am I going to need to solve for 3 unknowns? I'm going to need 3, right? I'm going to need 3. In each of the other examples, we ended up with only one unknown, A. So all we needed was one equation to solve for A, right? If I go back, see, that's all, when I go back to here, that's all I needed was this one simple equation, right? Solve for A, we're done. Yes?
So for the new problem, do we do that thing where we plug in 1 point for x and y and
Yes.
make the, like if we want to solve for a, we make b and c 0?
So you're right, something like that, exactly. So we're going to take each of these 3 ordered pairs. Now think what these are. What we do know about those is that they're solutions. They work, right? They're points on the curve. So those are values of x and y that are guaranteed to work, right? So let's just kind of color code these. What if we make this first one blue?
And one of them for sure is the vertex.
No,
Or the middle.
no.
So it could just be.
They're just 3
points
random
right
points.
next
Just
to
3
each
random
other.
points on a parabola. Yeah. Okay. All right. So attention up here, please. So if I use the solution x equals 2, y equals 4, what is that going to turn this equation into? If I substitute those values, substituting 2 for x and 4 for y, I get a times 2 squared, right? So I'm going to get a times 2 squared plus b times 2 plus c equals y, which is what? 4. Okay, or we could simplify that, right? And that's just gonna be, what?
4A,
4A plus
2B,
2B plus C equals 4. Okay, that is a linear equation, right, in 3 unknowns. How come it's linear?
That's not squared.
Yeah, because nothing's being squared. All the unknowns, which we could call variables if we want to, the unknowns are all taken to the first power, right? Okay, so there's one equation. Let's get another one. What if we use this point right here? So we'll make this our green equation. If I substitute in x equals 4, what is this first term going to give me?
4A.
16a, isn't it? 8 times 4 squared, which we can just simplify to a 16a. What about the middle term?
plus 4B.
4b, right? I'm going to get b times 4 plus c equals negative 4, right? Okay, if we do the third point, okay, what's that going to give us? If I substitute 3 for x, first term is going to give me
9A.
9. Everybody see that? 8 times 3 squared. 9a plus b times 3 is 3b plus c equals 1. Okay. Now, that's something you guys can handle, right? That's something we've worked with in a prior life, right? In semester 1, we talked about how to solve linear systems, even big linear systems. We have some shortcuts, right? Okay, yeah, now we could make short work of this using a matrix, for example, right? Okay, I am going to ask you to do one of these though. In an honors class, I'm going to force you to do a little thinking without the crutch of your technology. I'll give you some hard ones that you'll be able to use technology on. But how could we solve this thing without a graphing calculator? What could we do with this?
Times the top by anything you did.
Okay, yeah, we could solve this, right? Here's our linear system. Let's just identify those as equation 1, equation 2, and equation 3. Well, we could, but you guys don't know how to do matrix algebra without a graphing calculator at this point. So without a graphing calculator, using matrices is not gonna help you, right? But we can solve this. Remember how we dealt with a bigger system than a 2x2. Our goal, I'll remind you real quick. Our goal was we wanted to reduce this system to a 2x2 system, which is easier to solve, right? How do we do that? How could we combine, for example, 2 of these equations to eliminate a variable easily? Because that's our goal. What do you think? Sydney, you have an idea?
Isn't like the thing we did earlier where you kind of like the top equation back and
Yeah, exactly. Sure. Now, which would be the easiest column? C would be the easiest column to use, wouldn't it? Because those are always, the coefficients are always 1. So for example, I could combine, let's say I could combine equations 2 and 3, right? If I were just to multiply equation 3 by -1, I could combine those and make the C's go away. Isn't that really just the same thing? Now you guys can do this. Isn't that the same thing as just subtracting the terms, the pink terms from the green ones?
Yeah.
Right? Multiplying by -1 and adding is the same as subtracting. So you tell me then, we're going to call this the equation that we get from 2 and 3. What am I going to get if I subtract pink from green?
7A.
7a plus b
Equals -3.
equals
-5.
-5, right?
Wait. Which ones did you use with the 2 equations?
We used 2 and 3. Okay.
Where's C?
The C's went away because we're doing the equivalent of multiplying the bottom equation by -1 and adding. We're just subtracting the bottom equation from the top one, term by term, right? That's okay to do.
Did the bottom one subtract 2?
So,
Remember the third equation, or the second equation minus the third equation?
yeah, exactly. Second equation minus the third equation gives us. Now, I don't want to get into too much detail with this, but there is a property of linear systems. It's called principle of linear superposition. All it means, a fancy word for saying, if I add or subtract, if I add any number, how do I say it? If I add or subtract a constant times any of these linear equations to one of them, I create a new linear equation that is consistent with the system. It's also going to work, right? It's going to be a linear equation that would obey this system, right? So it's going to give us the same solution.
So 7AB.
Yeah, so we got an easier one, right? We got an easier one, 7a plus b equals -5.
And that
That's
becomes
an easier equation that's going to give us the same results as these three did, the same solutions, right?
Yeah.
Okay? Now I'm going to scoot this over just a
And
little
are we
bit.
trying to get two equations?
Yes, our goal here is when we're solving a 3x3 manually, we want to come up with two new, easier equations with the same two unknowns. That's a reduced system that we could solve, get that result and plug it back in and find the other unknown, right? So we ended up here with -5. Now what if we took, for example, equations 1 and 2? Couldn't I subtract the blue from the green also and get another equation, right? So what if we did that? Subtracting blue from green gives us 12a plus 2b equals -8, right? So there's our reduced system. This is an easy one to deal with. Now we could use elimination or linear combination on this one pretty easily. What could I multiply the top one, for example? -2, right? So if we do that, if I multiply the top one by -2 and leave the bottom one alone, that's just going to give us what? -14a
Minus 2B equals 10.
positive 10. Okay? Bottom one stays the same. So when I add those up, these go away. I get -2a equals 2. So what's a?
And then you can plug that back into a different one.
Yeah, good. So we can feed that back. Now we're still working on the 2x2 system, right? We got to solve the 2x2 system completely first. So I'll feed that back into, how about the top one? If I feed that back into the top one, I'm going to get a 7 times -1, which is -7 plus b equals -5. So what's b? 2.
Wait, where did you get that equation from the -7?
Right there.
Oh, okay.
And then you can just put that back into the third equation.
Exactly. So now we have b equals 2. If we have a value of a and b, now we can go up to the complete system and pick any one of those equations. How about the top one? That's pretty easy, right? Plug in those values for a and b and solve for c. Well, what's that going to give us if we do that? We're going to get
-4
Okay.
plus 4 equals 4.
-4 plus 4 plus c equals 4.
So C
So c is 4.
Whoa, I just missed that.
Okay, let's go back there. That's fine. So if I plug in a is -1 and b is 2 into this top equation, I get that result. I get -4 plus 4 plus c equals 4.
Oh, we're using all of them to plug into,
Yeah,
okay.
right. Because remember, that's our strategy. When we solve a big system, we're always just going to do a reduced system, solve that, and then use those results to solve the bigger system, right?
So then we put those back into the
That-
general form.
Right, so those are our answers.
You
Those
put
are the
this in
coefficients.
any form and you have an answer.
Right, well, now that we wanted this in general form, and so our answer is going to be y equals -x squared plus 2x plus 4.
So from that, we can find the vertex and all that stuff.
Yeah,
Is that our final answer?
that's your answer, though, but that's what we wanted. We just wanted the function that went through those points, right? So that's pretty cool. Think what we just did. That's a big deal. We were given 3 random points, and we were able to fit those 3 points to a parabola.
It's just a long process.
It is, but that's a pretty good thing to be able to do, yeah.
So are we gonna have to like take that and then do like the x equals -b plus or minus, and then find what x equals?
No, that's gonna be the answer. That's all you really have to do. We could, though. We could do anything we wanted with it, then we got the
But
function,
it's
right?
okay, just.
Okay. Okay, so real quick, though, does everybody see here? I wanna just remind you, how could we have done this one pretty easily if I had a graphing calculator? So I'm gonna show you a really good trick here. So I got something new for you, too. So So would you agree I could do a matrix method on this?
Yeah.
Hey, everybody up here, please. Okay, so we could go second, matrix. Now, what are the odds? I've already got this one entered. So there it is, right? 4, 2, 1. So I got 4, 2, 1, 4 for the first row, for example. Right? Okay. So I've already got it entered. You know how to do that, though, right? We're just going to enter each of these rows, as long as they're written in standard form. I just enter the coefficients and the constant in order. And then what? How do we solve a matrix system like this? RREF. Yeah, we want to put it in reduced row echelon form. So once we get that in there, all we have to do is go second matrix math. We go up to RREF. Oops. Right? That's why we're doing it again. So you'll be forced to remember it. So RREF of matrix A,
Oh, yeah,
right?
and then that's your answer.
Right? How about that? Okay. Now there is an even easier way. I'm going to show you a trick here. Okay, this. We're going to do more of this in, what's that? Calculator. Yeah. No, well, it's on the calculator, but it's even quicker.
We just found.
Yeah, but how do you know which one's A and which one's C and which one's C?
Because, okay, here's how you know. Because remember what this means. Don't lose sight of what this. When we represent a linear system in a matrix, each column represents its own coefficient, right? So here are the coefficients of A, the coefficients of B, the coefficients of C equals the constants. So what does this first equation really say? It says 1 times A equals -1. The second one really says 1 times B equals 2. And the third one really says 1 times C equals 4. Okay? And the way, kind of our shortcut way, remember how we looked at this? We looked at it in terms of patterns. We said if we covered up the last column, if we had that pattern of an identity matrix where we had 1s diagonally and 0s everywhere else, that always meant one solution, right? And those were the variables.
But if it was zeros.
If we had all 0s on the bottom, it was infinitely many. And if we had all zeros and a 1, it was no solutions, right?
Can
Make
you go
sense?
back to the matrix that you plugged into? Like
Sure.
when you go to the,
Yep.
so I can look at it.
Yeah. That's it. Whoops. That's it.
Okay, so we just plugged in just those equations?
Yep.
Oh,
4, 2, 1, 4,
okay,
right? 16, 4, 1, -4, right?
yeah.
Okay, so here's the easier way though. Watch this. This is really cool. So if we go to, now remember how we talked about earlier, we said at the very beginning of the year, we said that we reminded ourselves, it took 2 points to define a line, correct? Okay, and so we did a bunch of regression stuff where we put in a whole bunch of points and the calculator magically through regressional analysis, it'll give us the best fit line that matches those points. But what happened when we put in exactly 2 points and did regression?
Error.
No. Give us the exact line, right? Because 2 points, there is no room for error with that. If I put in 2 points, there is exactly one line that goes through those 2 points perfectly. And so it gave us back the equation of a line where the correlation coefficient r squared equaled 1, 100% fit, right? We called that a linear fit instead of linear regression because it was perfect. Now, what if we extended that trick to parabolas? How many points does it take to define a parabola? 3. So if we put in, if we wanted to fit a whole bunch of data that had kind of a parabolic look to it, we'll do this next chapter. If we wanted to fit that to the best fit parabola, we would use quadratic regression, and hopefully we'd get back r squared equals 0.999 something, right? So we get a really good fit. But if we put in exactly 3 points, it's going to be a perfect fit, and it's going to tell us what that parabola is, right? So we can just go to stat. I don't need second, do I? So we just go stat, edit, and what are the odds? I've already got those points in there, right? Now all these are, look what this is. These are the 3 ordered pairs corresponding to our 3 points, right?
Wait.
Remember we always put X's in column L1 and Y's in L2,
Yes.
right? Okay, now, if I just go stat calc 5, not stat calc 4, I'm gonna go to quadratic regression. Okay? Look what happens. Mine looks a little different, but look what it tells me. Y equals ax squared plus bx plus c. A is -1, b is 2, c is 4. That was familiar, right? And r squared equals 1.
So, to do that, can we show me again, you go
Sure.
to stat,
So we just go, all we do, hey, listen, why am I babbling this all the time? Come on. So we just go stat edit, we put in the 3 points that define the parabola. We go stat calc 5 for quadratic regression, and it gives us back the equation. Okay?
Stat calc 5.
Yep. Now this works for any case where we have 3 points. So I could even do this, for example, on our previous example, where we had something like that. It would work, right? I've got 3 points, so it's going to give me back the answer in general form, right? So that's the one thing. Quadratic regression always gives you general form back, but a lot of times that's what you want, right? How could we use this for the examples that we looked at for vertex form? Like, for example, if I pull this up, no, where was that? Right, was it there? No, shoot. I'll pull up another one. So for vertex form, what about that one? How could I make quadratic regression work here? I'm only given 2 points. Yeah, I get a third point though, don't I?
Yep.
I could reflect that over and get the third point for free, right? And then I've got 3, and I could do quadratic regression again. Now the disadvantage of this is, with the TI-84s, unfortunately they don't give. There are calculators that will do this. This one won't. It always gives us back decimal answers for our coefficients. So if we want to exactly fit the parabola, this isn't going to help us because it's only giving us decimal equivalents. Like if they were supposed to be square roots or something, we're stuck.
So if we wanted to just have it exact, should we just stick with the first one, the matrix?
Yes, if you want exact answers, you'll use the matrix method, right? Okay,
So
and it'll
can
give
we
you
just
back
do it
fractions,
anyway?
for example, because we can always turn the matrix results into fractions, right?
Yeah, so can we just do that anyway?
You could, yeah, you could. Okay, yeah.
My calculator doesn't have the R squared, is that bad?
Okay, it's easy. All you have to do is turn on diagnostics on, stat diagnostics on. Yeah, easy to do. I'll show you. Okay. All right, I think we're good.
what is our square?
R squared.
Wait,
Can you remember what R